Hello, good evening all. Gokul, you are able to hear me?
Yes, sir. It is fine.
Gokul?
Hello. Yeah, it is audible, sir.
Okay.
Audible, sir. Hello.
Start session. So, a recap of yesterday. What we saw is how to load raw data, how to convert it into a time series, and we had a data called yeah, yesterday's work. So, and there's raw data. This raw data looks like. So there is energy consumption. That's a synthetic data for our work, right? And finally, what we did next is convert that particular data into a time series data, because in our package we need to define specifically that it is a time series data. So we have taken that as time series data, only the energy column. And after that, we created some other data points or the columns so that it understands what is month and what is energy, or what is the time quantity and what is the data quantity. Okay. So then we plotted the data. The data was something like this. And then we saw that there are a lot of highs and low. The data is not so smooth. Okay, so in order to apply or we see in real time, the data would be much different. It will have much more noises. Okay, so as it is a synthetic data, we are able to do some easy, I would say, smoothing efforts, and we are able to smooth that data. Then we plotted the smoothened data, that is using the moving average, we smoothen the data and we overlaid that particular data to the raw data, that is the real data. Okay, and we were able to see like, okay, it fits, okay, to a greater extent. Okay, then see, it is not only about the data what we are having, why we are fitting the data with another derived data is we want to match our model to the real data so that we can predict the future data. Okay, so we try to predict the future data, and the predicted data also we try to plot over the real data, and we were able to see like more likely we were able to fit the data. Okay, now one especially in this forecasting, after doing all this work, we have to see the validation of the data, right? So yesterday we saw about the CRISP-DM framework, and in the CRISP-DM framework, we know like the model has to be built, data has to be cleaned. Here, the smoothening or the moving average is the data pre-processing what we did, and after that we created a model. Okay, and the model we overlaid with the original data, but post that we have to see whether our model is okay. Okay, so this is the CRISP DM framework what we discussed yesterday, and you can see here validating the model is very important. Okay, so that validation is something which we tried. Okay, okay. Administration check. So, so that is a small introduction about a different type, why we are more interested with analytics, especially in this decade or the decade to come. Okay, and what is descriptive analytics? That is something which we have seen. We discussed about two type of data processing or the database availability. One is the transactional data, and another is the data warehouse. We call this as data warehouse. Okay, and data warehouse is where we were able to have the data in a format, a specific format, so that we can do the OLAP operation. The OLAP operation okay, and I want the data of say HVAC.
Team, there is a connectivity issue for Somu. He'll be joining in another minute.
Sorry, some connectivity issues. Okay, got disconnected. Okay, fill the you able here, right? Hello, Hemanand or Gokul, can you respond?
Yeah, now it is
Am I
audible.
audible?
Yeah, it is now audible.
Gokul, am I audible?
Yeah, it is audible, sir.
Okay, okay. I think the
Hello.
hello. Hello. Hello. Pradeep, you're able to hear me now?
Yes, sir, it is audible now, sir. Your screen is also visible.
Pradeep? Okay, okay. Okay, okay, okay. Okay. Some connectivity issue. Sorry for that. Okay. So the slicing, dicing, and other things are part of the OLAP operation. Okay, and process the data, and it becomes very easy for us to visualize the data and create beautiful dApps like this. Okay, so just to show you, you can see here. I am seeing only the HVAC. You can see the HVAC. This is a ribbon graph. This is called ribbon graph. So you can see here the HVAC have risen during April and May. It is very obvious, right? During that time is summer, and obviously the temperature will be high, and you will be needing more heating, ventilation, and air conditioning. So that is how the data analysis happens. Okay. Try to install Power BI and do small kind of exercises. Okay, fine. So till that we saw yesterday where we did some exploratory data analysis. Okay, and today what we are going to do is do a small forecasting. Okay, and there are many methods of doing forecasting. Okay. So there are some naive methods, that means very simple methods. So normally in any company, if they want to forecast how much will be the energy demand for next month, what they will normally take is they will take the average of say last 6 months or last 12 months, and they will say like my baseline energy demand will be something like this. Okay, why this is energy forecasting is important, or why energy forecast 50,001 is something everyone follows for energy management system, and ISO 50001 requirement says like you need to have a baseline. Okay, there has to be some benchmark data over which you have to compare your energy indicators and take actions according to that. So a good forecasting model will help you, and based on that you can take action and you can comply with the many standards like ISO 50001, and it will be very easy for you also explain to people like this particular rise in energy is because of this, and this I have seen it even before, like the HVAC example which we saw last time. Okay, we can tell to the management that so this is during summer. Last year also we have seen like that is increase of this many percentage. Forecasting is very important. So some of the very typical methods of forecasting what financially people will be using is having a trend type of forecasting. That is also people do it, and moving average. That is also people will sometime do it, and they will also see some seasonal effects, and based on the seasonal effects they will do the forecasting. So yeah, over period of time the production might have ramped up, say instead of 2 shifts they might have run 3 shifts. Instead of say 50 machines they might have done some consumption raised. Okay, so capacity enhancement or fully utilizing the capacity. Okay, see we treat the data, but the ability. So I have shifted my place, thinking like I will get some other tower where traffic is less. Let's see how it works. Okay. Sorry, yeah, not able to hear you. Anand sir, I think now it's okay. Yeah, now it's okay. I'm sorry. I'm very sorry for that. Okay, fine. So forecasting, why forecasting is needed. Okay, so that is one for the ISO 50001. Second is for the IEX. Normally we will have that energy trading, okay, kind of things, especially the solar, wind, and other things. There also forecasting is very important. Like share market, how we are predicting how the prices will be there per share or something like that, or the Sensex or something like that. The IEX is another share market for energy specifically, and there also forecasting plays a very important role. And sometimes we lose money if we forecast a different demand and bid for energy, and finally you might end up consuming less, okay, or something like that. Okay, so that will create a financial impact. So these kind that is the why forecasting is very important. Okay, so conventional forecasting will not. Okay, so we have to do a deep forecast, especially see the seasonal effect, see the cyclic effect, see what is the trend going on. Okay, and we also have to keep in mind, or I would say neglect the intermittent demands. That means we have to filter out the peaks, like how we did the smoothing of the energy demand in the our previous R exercise. So there will be some intermittent spikes which also have to be filtered. Ideally, if you say these are all outliers, these outliers should not be normally taken into account, okay, for forecasting. Now, there are different methods. Okay. So there are different methods. The naive method, I told, like, okay, it is just what in last year, what is the consumption of May month this year? I will have the same answer. That's a very simple, straightforward thing. Okay, so and there are the moving average way of forecasting, and there are something called weighted moving average type of forecasting. See, why this weighted moving average type of forecasting is very important compared to a simple moving average is moving average. We know, like say we can say like last 3 months average. I will be taking for predicting how much will be the current month energy consumption. Okay, so that is the simple moving average. A simple average is average of say last 12 months. Okay, so moving average is something like so I will have only the last period. Okay, when we are talking about weighted moving average, we take into account or we give weightage for the very recent data. So when I am taking the moving average, say for 0.123, I will give the weightage for the last month more compared to the last but one. So say I'm having something like, okay, I will give a weightage of say I think it's that the subsequent slide. This is the simple average. Yeah. Okay. So you can see here the last month I am giving more weightage when I am computing the moving average for predicting or forecasting my current month. Okay. So this is the weighted moving average. So instead of having 1, 2, 3, sum of the 3 divided by 3 will be my next month prediction. I am using a formula which gives more weightage for the just last month data. Okay, so this is the weighted moving average example. Okay. So now I don't want to just jump into the R code and just to show you some things. Okay, so try to uh, make some Excel sheets where we can explain okay how this calculation works in Excel, so that you understand better why this is needed. Oops. Or you can even use this Excel straight away. It's not a very big deal. Okay. So same. Let us see first a simple exponential smoothing type of a forecasting. Okay, so I have here column A is my month. Okay, column B is my energy, that is actual energy what it has taken for the particular month. C is the forecast what I'm doing, and SC is the standardized error. Okay, so a square root of the error. Okay, why square root? Sometimes it will be plus, sometimes it will be minus. The error is nothing but error is nothing but the difference between the actual and the forecast. Okay, and square root of the standard error is nothing but the error cap 2. Okay, so I am just squaring it so that if it becomes negative also, I get the error value or the absolute error value. Okay, and then another indicator for calculating error is the mean absolute percentage error. We call it as MAPE value, MAPE. And normally in the R type of, or when you're doing a professional forecasting, this MAPE value will be the target value when you are tuning your forecasting methods. Okay, in machine learning or data science, they will say like it's called hyper tuning. So hyper tuning, that needs to be a target value for which the hyperparameters will get tuned. Okay, so the hyperparameter tuning happens with the target value. Here also, I will show you an example using the very simple data solver technique, how we can do it. Okay, so this is now we saw the weighted moving average with an illustration. This is called exponential smoothening. Okay, so an exponential smoothening is having a formula, something like this. Okay, so the forecast for the next month will be equal to alpha. Alpha is a value. Okay, this can be between 0 to 1. Okay, multiplied by the actual value of that month plus 1 minus alpha of the forecast of that particular month. Okay, so this is a method called exponential smoothing. Okay, so let's see how this is getting calculated. Let me leave the first 2 months because hardly we don't have a history of data. Okay, so let me concentrate from the month 3. Okay, month 3, you can see here the formula. So I am using IS. Okay, I column, sorry, I2, that is I column. Second row is 0.5, which is my alpha value, and I'm dollaring it. That means when I extend the formula, it will not change. That means when I'm extending to row 5, it will not go. Okay, so I'm dollaring it with an equation with a dollar, and into B3. B3 is my DT. Okay, DT is the actual energy of the last month. Okay, plus 1 minus alpha, 1 minus I2 into C3. C3 was my forecast for last month. Okay, so my forecast for last month was 160. My actual energy for last month was 175. With these two values, I'm calculating how much will be the forecast for the third month. Okay, similarly, I have just extended the formula. Okay, just extended the formula by just dragging it to the next row. Okay, and this is the exponential smoothing kind of a forecast, which is the next step of weighted average, weighted moving average forecasting method. Okay, and we calculated something called the standard error. Standard error is nothing but the actual value minus the forecast value squared. Okay, and MAPE is nothing but the absolute value of B3. B3 here is the actual energy minus C3 is the forecasted energy divided by the actual energy. So how much is the error with respect to the actual value? Okay, and I'm just absoluting it so that if the error becomes minus or plus, okay, it becomes a real value for me, and I have just selected that as percentage in the type of data, so it is up as percentage. Okay, like that I have just forecasted, and you can see here this is my graph. Okay, series 1. Okay, series 1 is my actual energy, what you are seeing, the B column. Okay, and series 2 is my predicted or the forecasted energy. Okay, so I'm having something like an alpha value of 0.5 here. Okay, so I told about this hyperparameters. Like here the hyperparameter is alpha. Okay, so this alpha I can have it either 1, okay, or I can I don't know, 0 doesn't work here. Yeah. Okay, 0, that means it will not do. It is a flat type of forecast. Okay, so it is a value between 0 to 1. Okay, so I can have 0.6, need not be 0.5, but what is very important for me is this particular value, root mean square error. Okay, so what I'm doing is I have the SSE, that is the squared error. Okay, the average of all the squared error, and I am taking the square root of the average of the squared error. Okay, so that is my root mean square error, RMSE. Okay, root mean square error, and I am also calculating the MAPE value, which is nothing but the average of all the individual MAPE values. MAPE is nothing but the mean absolute percentage error. Okay, so this is the way how we will see how my forecast works. Okay, so see, obviously this is only a line of command in Python or R, but unless otherwise we know how this is happening, it will be difficult for us to understand. Okay, and weighted average, I showed you how the thing is. I think moving average is very simple, you all know. Simple average also, you know. Okay, and the next method is called the Hole's method. Okay, but before going to the Hole's method, let me just show you how this hyper tuning happens. Okay, hyperparameter tuning. Okay, so here the hyperparameter I told that as a alpha. Okay, so I want to see which is the good alpha value, so that my root mean square error is less. Okay, so I want the root mean square value to be as less as possible. Okay, so what I'm doing is I am going to data. I have my solver already here. Okay, and in the solver I'm creating an target search. Okay, so the target here or the objective here is I10. I10 10 is my RMSC here. At present, the value is 17. Okay, so I10. Okay, so I10. Yeah. Okay, so I10. I want that I10 to be minimum, as low as possible. And how I want to do this, I will change I2. I2 is my alpha value, which is my high. Okay, and if I say like, okay, you find me a value so that I get a very small RMSE, sometimes it will give some value like a -1 also. Okay, who knows? Okay, or sometimes it will go even more than 1. Okay, so I want to tell to the model like, boss, you cannot do a parameter search just like that. You have to keep some constraints in your mind. The constraint 1 is I2, which is my alpha value, should be less than 1. Okay, and I2 at the same time have to be greater than 0. Okay, so it has to be less than, it has to be a value between 0 to 1. Okay, so that is my. Okay, there are many methods of doing this. Okay, so I'm just selecting the default value, which is the GRG non-linear. Okay, I haven't tried other things to verify. Okay, so now I will ask Excel, boss, please find me the good alpha value so that I get a less RMS. Okay, root mean square error. Okay, for my forecast, and I am asking it to solve. Okay, and you can see here it has solved, and it is asking me whether you want the value to be kept or you want to restore to the original value. So what it has done, I think it was somewhere around 5 or something. Okay, so now it has selected a value 0.106 as the alpha value, which has given a RMSE value of 16 and a MAPE value of 8. Okay, so I'm saying like, okay, keep the solver solution. So this is the solution what Excel has given me. Okay, so and I am doing, and just asking it to give me the report also of this. Just I want to show you. So you can see here. So now I got this value. Okay. So and I'm also showing there are some reports also gives. Okay, so here in this particular case, it is a very simple one, but when we are doing price analytics or marketing analytics, that will be very helpful, which will say like the price of this product should be between this, the price of or the sales of this product should be between this to this. Okay, here the parameters are very less. Okay, but it will also throw and report. That is what I want to give you. So especially for the energy fraternity, when you're doing an energy auditing, when you're doing an assessment of the things, okay, these kind of reports also will be part of your right. So you can add these kind of reports also, and just copy these reports and you can use it in your things. Okay, so now you can see an alpha value is 0.1 is better for this particular uh, forecasting. Okay, so that's about here. Okay, so this is on the exponential smoothing. Now let me go to the next complex one of a forecasting method. uh, See this exponential smoothing, what it has you might have seen here. See, it is only doing something like a trend. Okay, you are not seeing the forecast having some variations. Okay, so it will not take the seasonal value variations into account. Okay, so that is the, I would say, the disadvantage of this exponential smoothing. It is a simple method. Okay, so next let me go to the, okay, so next let me go to something called Hall's smoothing, HOLTS. So want to choose the formula for this. Okay, so let's see Hall's method formula. Yeah, yeah. This is your Hall's method formula. Okay. Yeah, this one. Just right here, so that we will not save this. Okay, so again here, you can see here it is not only taking the trend, it is also taking the seasonal things into its mind. Okay, so that is the advantage of a halt seasoning, HOLT, halt seasoning method. Okay, or forecasting method. So here, it is also very similar to the previous exponential smoothing, but here instead not only level we are seeing here, we are also seeing something called trend also in the things. Okay, so that is the only difference here. Okay, so what? Everyone able to hear me? I think everyone able to hear, right?
Yes,
Yeah.
sir. It is audible only.
Okay. Okay. Fine. So here what we are doing is we are adding that trend value also here. Okay, so again here also I'm not considering the first three here periods. Just change that as months. Okay, and this is the energy actual data, and this is my forecasted data. Okay, so how this forecast happens? Okay, let's just see the fifth month forecast. Okay, so the fifth month forecast actually does the sum of the previous or the forecasted value for the level of the previous month and trend of the previous month. Okay, so now let's see how this level is getting calculated. The level is a simple exponential smoothing kind of forecast. That's all. What it does, it uses the same alpha value and the 1 minus alpha value for the forecast. So alpha into the previous month data or the actual data plus 1 minus alpha of the previous forecast. Okay, so that is the level. Okay, now what is the trend? Trend, there is another hyperparameter called beta. Okay, so E2 is the beta value, is D9 minus D8. So D9 minus D8, that is the previous trend, plus 1 minus beta into E8. E8 is the previous trend value. Okay, so this is the value which it also calculates. That means it is also seeing the trend value. Okay, and it is calculating what would be the next month's forecast. The next month's forecast is 88.14, which is the sum of 81, which is the level of the component of the forecast, and the trend component of the forecast is 7.58. Okay, and it uses the formula. Now, just nothing seasonal. How we will calculate now again? Alpha, beta, you have one more gamma value, and you need to have this particular formula. That's all. Okay, so this is the calculation it does. Okay, it is nothing complex, no calculus or nothing is here. It is simple calculations which is doing this particular forecast. Okay, here also let me try using the solver. Okay, so I want where is my k? Yeah, k, that is my root mean square error. Mean square error. Here also I have the square root error and the MAP value here. Okay, and I want the root mean square error to be less. Okay, and by changing here I have two values. What is the two values? One is D2, which is my alpha value, and E2, which is my beta value. Now, when you add the seasonal, you can have your gamma value as F2. Okay, so that is also possible. So I will attach this into the chat so that you can also try to use it. Okay, so this calculation, how the MAP value is getting calculated, how the square root error is getting calculated, though it is simple, it is better to understand it. Otherwise, it will be only a black box, and when people ask you some questions, you will not be able to answer it. Okay, so here I'm just giving one thing is like it has to be less than or equal to 1. At the same time, I'm also saying like the variables should not be non-negative. Okay, that means it has to be always positive. Okay, so and I'm just selecting. Okay, you can select multiple things. Okay, I'm using evolutionary just to show you the variance. See, our final objective is having a lesser RMSE values. Okay, so I'm solving it. Okay, let's see. It will take some more time because you need you have two parameters. Okay, and I'm asking it like I need a report also. Okay. Okay, and it is now saying an alpha value of 1 and a beta value of a 0.18 is giving you an RMSE of 8. It's a good value. It's 8 is the value it is showing, and I'll be able to use it. And I want the report also. Okay, I'm saying I want the report. It has given the report. Okay, so in the report it will say like, okay, my alpha value and the beta value, the best value for a very good thing is 1 and 0.18. Okay, I mean, and it has tried multiple values, right? So what are all the values it has tried? That also has a summary it is going to give you. Okay, and you have something like called the answer report, which will see here it is the different data it has used, the population report. Okay, here it is the output what you got based on the simulation. Okay, so the simulation gives a very less RMSE value. Originally it was 17, but after optimization it was 8. Okay, and the best value of alpha and beta is this and this. Okay, and what all the constraints used, that also you can show here. See, why this is important is when you are submitting this particular thing to your client or adding it to your report, you need these things also to be mentioned. Okay, so this also gives a standard report, just a copy and paste it in your report, so it becomes a crystal clear report where everything is answered. Okay, so now you might have understood what all the different methods okay of a forecasting. Okay, and the another widely used method or method is called okay. So AR stands for auto-regressive. Okay, and MA is actually moving average, but it is not. I would say I don't know where it got this name, but actually here we will be having something called ACF. Or something like that. Okay, so these kind of things are there. Okay, which you will see in the subsequent slides. So this is there are the next method of a forecasting is called the ARMA method, which is autoregressive moving average method. Okay, which we are going to see. Okay. Okay. Okay, so this is the widely used method, I would say, like everyone uses this. Okay, ARMA method. Okay, so AR is for autoregressive and MA is for the moving average. Okay, and ACF the is a very important factor here called the autocorrelation factor. Okay, there are some examples people have given here. Okay, so I'm not going to use this example. I have my own example. Okay. So now, where we were, yeah, okay, fine. So what we have done is we have created a model and we have mapped this particular model and we have used only the cyclic variations and the seasonal variations and the trend variation. Okay, so what happens is the ups and downs. Okay, I think you are able to see my cursor. Okay, this is your, what is this? This is the cyclic one, the seasonal one. Okay, and after that you have something like you're going way high or something like that. Try to use it. Okay, so ups and downs is your cyclic and seasonal variations. Okay, color different. Okay, and you are having something like a trend. Okay, okay, so what we okay, so this is the cyclic, seasonal and the trend. Okay, fine. So cyclic, seasonal, trend, and what is the next thing is the okay, this cyclic, seasonal and trend is called the global values. Okay, it's called the global pattern. That means it is there throughout the um, data set. Okay, and you have something called local. Okay, so local is nothing but yeah, random noise or a noise. Okay, noise. Okay, so how to get the noise out? Okay, so the local is equal to actual data minus the global predicted data. Predicted data. Okay, actual data minus global predicted data is local data. Okay, so let me do this because we also have to understand why this noise or residual is also there. Okay, and we have to analyze that particular residual. Okay, so this residual will have something called the partial autocorrelation or the autocorrelation kind of behavior. Okay, so if I'm able to identify that there is an autocorrelation behavior, I can also model that. Okay, and that is also needed. Okay, otherwise we have to answer for this particular. See, we have to. Okay, we have to answer for this particular whatever gap is there. Okay, So compared to the prediction. Okay, so I want to find that answer also, right? So I need to find what is that noise. Okay, so how to find that noise? That is what we are going to do here. So I have predicted the data, which is my red one. So global prediction minus the actual time series gives me like local prediction. Okay. So my actual data is my time series data. My global predicted data is the data what I use to develop the model, and the remaining one. Let me see what is my remaining one. Okay, and how it is. Okay, so the remaining one. Fine. So if you can see, the range is 0 to somewhere around 800 megawatt hour. Okay, and but the local value or the noise value is somewhere between say minus 60 to somewhere plus 100. Okay, so there is a component or a considerable amount of component I'm not able to predict, and it is having a range like this. Could be like 150, and my actual range is somewhere around 800. So almost 10 percentage or of the value I'm not able to predict. Okay, so I want to also predict that. Okay, so for predicting that, I have to see what is my ACF values, the autocorrelation values. Okay, so this is one of the function we use to plot it. Okay, so what it does is it is giving the covariance, the value which gets varied because of the just before value or the its own set of value. Okay, so that is the autocorrelation. So the autocorrelation here, okay, which gets calculated, and this is the thing, the function ACF computes, estimates the autocovariance or the autocorrelation function. Okay, you have function PACF, which is a partial autocorrelation function, and there is one more called CCF, which computes the cross correlation or the cross variance of two univariate series. Okay, so that is the thing. Okay, so what I am seeing here is the autocorrelation of the whatever value I'm getting. Okay, and there are some parameters called lag values, and the lag values how this is the limit. Okay, the blue one is the limit, and when it crosses the limit, this is something which we have to address, and this has to be brought down. Okay, only then I can claim successfully that I have predicted considerable amount of local component of my data. Okay, so that is what we do. Okay, so for doing that, okay, so for doing that, this is the partial ACF. Okay, so I want all my values to be within this particular blue line. Okay, the control limits. Okay, so what I'm doing is I'm using something, a function called ARIMA. Okay, which is nothing but what we have discussed, which is the auto regressive and moving average autoregressive and moving average function in R, okay, which models the time series data. Okay. Okay. And and there is some other things called the Akakai information criterion and Bison information criterion. These are all the values which is used to fit the data. Okay, so this is nothing like how we have used the solver. The same way, these are all some of the methods which is used for searching the best fit hyperparameter for a given data. So if I give a data and I call this particular from function ARIMA, auto ARIMA, it's not ARIMA. If I have ARIMA, then I have to mention the values. Okay, I have to mention the hyper values, alpha and other things what we have seen in the Excel example, similar to that. Okay, but when I say auto ARIMA, it does this particular computation or searches the best hyperparameter itself. Okay, so I am calling that particular function, and it does your work. And let us see what this AutoArima has done. Okay, so it gives a report after doing its work. Hey, boss, I have done this. I don't know. Okay, previous function is yeah. So here you see here. Okay, so now you can see here the residual value. Before it was at a different level. It had first mapped what is the residual value, how it was, okay, with respect to the time, that is months. Okay, so this is nothing but the data what we had, not the standardized value. Okay, so we have seen somewhere around minus 100 to plus 100 in our previous graph of local prediction. Here what it does is it standardizes, okay, and it plots a value between -2 and 2. Okay, and it has seen that there are ACF of this particular lag value, one at 0 and another at somewhere here. Okay, and it has found a way to remove the autocorrelation functions, so and add it to the prediction, so that we are able to see a best way. Okay, so just to compare this with our previous things, yeah, you see here, so the same ACF value only it has used. Okay, and the standardized value you see here, it is -100 to +100. Instead of that, it has used -2 to +2. It's nothing but the standardized value of the residuals. Okay, so this was my residual, this was my ACF, and this was my p value, and the p value is normally used as the indicator. It has to be within some limit to claim that my model is good. Okay, so here let's see how the p value is. Okay, this is somewhere in 0.8 or something like that. Okay, so now I know that this is my AutoArima output. Okay, and this is my AutoArima output, and I have this AIC value of 740.39 and the BIC value of 742.66 log likely put, and these are all the parameters which gives me the best or the performance of my AutoArima value. Okay, so now I want to eliminate whether I have maximum enough to remove the autocorrelation and covariant data. Okay, which is mathematically I can model it. Okay, if I remove that autocorrelated and covariant data, rest other things are noise. Okay, and that noise I cannot model it because that is not part or that is not having any pattern. I cannot mathematically model it. Okay, but I have to check whether my residual is a real white noise or not. White noise means a data or a pattern which I am not able to model. Okay, so that is the next check what we have to do. This is the model validation what we have to do it. Okay, and this they call it as whether the residual is stationary and other things. Okay, and it has a test called ADF test. Okay, there is a test which does so. Residual is nothing but my local predicted value minus whatever my AutoArima had found. Okay, the fitted ARMA fit is nothing but my AutoArima, that is the auto regressive and moving average type of forecasting, where it has predicted like this is the local value, and whatever rest or the component in the local value which can be a model, whatever away from this is a pure residual which I want to climb, or I want to say that whether it is white noise. Okay, so this is the test called ADF test, which is widely used. Okay, so let's see what is this ADF test. Augmented Dickney Fuller test is normally done for to see whether the noise is stationary. Okay, so I want to see whether it is stationary, and I want to see, and there is one more test is also called as a KPSS test. Okay, so these are all the two tests which people widely use. Okay, this is test for stationary, and this is also a test for stationary. Okay, so what it says, it gives me a p-value of 0.04, and here the p-value is 0.1. Okay, so actually p-value, what people or for assays, what is the null hypothesis? Okay, hypothesis. I say like the residual is a noise. Okay. Okay. Alternative something else. Okay. So P low, um, that means that means what that means HO go HO go. Okay. HO is my null hypothesis. HO is my null hypothesis. Okay. That is for the test called ADF test. Okay, so here I am getting P low, that is 0.04. That means less than something 0.05 is good. Okay, so it's P low. That means my null hypothesis cannot be proved with evidence. Okay, sorry, I'm sorry. Here is not a noise. Okay, is not a noise. Okay, that is my null hypothesis. That means this particular person is not a criminal. That is the null hypothesis when a person is taken to the court. Okay, the alternate to that is there is a subsequent there is enough evidence to prove, or there is not so enough evidence to prove that this person is not a criminal. Okay, so that is the alternate of this. Okay, so here in this particular test, it is a p-value. If it is low, that means the model or the test cannot prove me that whatever residual I am having is not a noise. Okay, that means the alternate hypothesis it holds good, or no one have challenged the alternate hypothesis. So I feel like whatever residual is there, it is noise. Okay, that is for the ADF test. But for the KPSS test, it is actually the ulta. Okay, KPSS test, it is actually the ulta. It should be there somewhere in the p-value or interpolated. Okay, it's not that, but it is actually the ulta. If the p-value is higher than 0.05, that means I can say like my residual is noise. Okay, so these are all the two tests which is done like whatever prediction I have done. After that, I have done auto ARIMA, that is autoregressive and moving average forecasting. I even after that I am getting some data which I am not able to model, and I want to quantify that particular model as pure noise. That means no one can model it. Okay, therefore there are two tests. One is the ADF test and another is the KPSS test, which is widely used, and this gives a result, and we have to see this particular p-value, which gives us the indicator whether it is noise. Okay, whether it is a pure noise. Okay, so now what I'm doing is like initially you have seen like the initial data. That is my raw data. Yeah, raw data was having 77 observations. Okay, and the data what I used for modeling was having 71 observations. That means 6 months of data I haven't shown to my model. Okay, so now I want to check whether boss, now the remaining 6 months data, I want whatever model I have developed should predict the remaining or forecast to a greater level compared to the real value. Okay, so the raw value was having 77 months of data, but for the modeling I have taken only 71 months of data. So the remaining 6 months of data, which is the out data, okay, of 6 months, I'm going to predict and compare to the actual whether it is good. Okay, so now let me predict it. So what is the prediction? The prediction is I have modeled the data already, and using that I'm going to do the prediction. Okay, so the global prediction I have done it, and that I'm moving that to a variable called fcast. Okay, and I'm seeing the map value like in the Excel, how in the Excel what we have seen is like the view of any model, okay, any accuracy of this particular library called forecast, okay, is used for checking the accuracy of things. And how it checks the accuracy? It checks with respect to the hidden value. Here I am having 6 data which is hidden, okay, and with that it is calculating the MAP value. Okay, so what I'm getting is somewhere around 39.90 is MAP value what I'm getting. Okay, so now what I'm doing is just that is the numerical way of seeing whether things are in place or good. Okay, now let me do it in the pictorial way. Okay, so previously what we have seen, yeah, see, you can see here it is only 71 months of data, okay, what we have used, okay, time series data. Okay, now what we are seeing is the 77 months of data. That means this new data is now introduced, and I have done the prediction, and I am seeing whether the prediction is right, and I have calculated the MAP value. Okay, but here I have used only the LM-fit function, that is the global prediction function. That is LM-fit, yeah, LM-fit is nothing but my global prediction. So now, as you all know, AutoArima gives my local prediction also. So doing my local prediction. Okay, so let's do the local prediction and add it to the value. Now see what is my MAP value. You see here, now the MAP value has got reduced. It is 34.1. So previously, only with my global prediction, my mean just a minute. Okay, yeah, yeah, mean noted that down somewhere. Yeah, mean absolute percentage error. Mean absolute percentage error should be as less as possible. So now, before only with my global prediction, it was somewhere around 36, and now it is 34.1. Where is my 36? It was 39. You see here, only with my global prediction, it was 39. Now, along with my local prediction, that is the AutoArima function, I'm seeing a MAP value of 34.1. Okay, so let's see it visually also. Yes, visually also it is like this. Okay, so this is the advantage of using forecasting here. Okay, now see, there are something very easy to do something like that, and when pictorically when we are giving the data out, we also have to give some confidence interval. Okay, it should not be like the exact value. Okay, there will be some plus and minus the forecast will have. Okay, that is the limits that we will have. Okay, so that limits also we have to show. Okay, so here instead of using the earlier data, I'm using data which is normally available with the forecast library. Okay, forecast library. Okay, it has a lot of data, wine production data, some wool production data, and there are some other data set also. And one of the data is gas data. Okay, UK gas data, which I'm going to use now, okay, as the next example, and I'm going to show you how the forecast will look like. You see here now, so whatever is in blue, whatever in blue is the forecasted value, and this blue, you see here, there is some light blue and dark blue which is hugging the line. Okay, so that is the limit. That means the forecast can go between this and this. So that is the limit normally we will say. And here I am forecasting the UK gas consumption for next 10 months. If I want to say like, hey boss, please do it for next 15 months, just I have to change this particular H value here and ask the forecast model to do this, and I will get for the next 15 years of data. More the years from the current the confidence interval will change. That means you will have a wider thing. Okay, so you can also forecast for next 2 years also, not a problem. Okay, next 2 years, that is also possible. Okay, so this is about how to use the auto plot function. um, just nothing doing, don't do any calculation of local data or global data, just give a report to your customer using the auto plot function, and give them like between this to this will be your variation of say here it is UK gas consumption. You can also say like this is this the same data frame you can import inside, which could be the petrol consumption or the fuel consumption, the boiler wood consumption of any say poultry, or the coal consumption. Okay, all these things you can have it inside, and without having any multivariate analysis, univariate analysis, only the data and the time, only these two parameters only keeping in mind, you can do the time series forecasting and give impressive reports. Okay, so this is the end of our session on time series. Okay, any questions? I'll be happy to answer. Probably Gokul, you have to unmute everyone. Okay, so if there are some questions, let us ask.
I have unmuted this. Participants can unmute themselves and ask.
Maybe for those who have some hearing issue or the audio issue, probably Gokul will be uploading this recording in YouTube, and he will share the link. Okay, probably you can go to it. So I am copying this codes into the chat window. Okay, and posting it for you all. Okay, and you want the files also, right? So adding the files to you. So this is the data what I have used, and the R code. Okay, data set for you. The examples also.
Can you hear me?
Yeah. Yes, sir. Yes.
Hello.
Yes, sir. Hello.
Somu, can you hear me?
Yes, sir. Yes, sir. Yes, sir. Please go ahead, sir.
Yeah, what I see from the basic data, 71 or 72 months data. Is that right?
Yeah, the original data was having 77 months. For the model building, we have taken only 71 month, and the remaining 6 months we predicted and we validated it with the MAP value.
But in real situations, how effective will this blend changes, product quality changes?
See, sir, any judgment whenever we are doing some audit or something, whatever evidence is given to us is taken into consideration. Whatever is the historical data given to us, and based on that, we are creating a model with whatever evidence is available with us. With that, we are doing the forecasting. Obviously, when there are changes in the scenario, say scenario like this COVID situation, which is apart, it cannot be forecasted.
I can.
Okay, so I have added the Excel files and the code also, so that you can practice sake.
No, see, my point is, during energy audit, we have got to be giving energy saving on an instantaneous basis. Hello?
Yes, sir.
Hello?
Yes, sir. Yes, sir. Please go on, sir.
Hello?
Sir, I'm able to hear you. Please. Sir, Mallikarjun, sir, please go ahead. I'm able to hear you. Okay, no problem. Mallikarjun, sir, we can connect later and we can have a discussion. Not a problem. Any other questions? Okay, so if there are no questions, next session, we are going to see a data set which is yeah, performance of a combined cycle power plant. Okay, and we are going to use that particular data, and we are going to predict how much will be the output from a combined power combined cycle power plant with whatever data is available. Okay, so that is a famous data set which is available, and with that we are going to see the simple linear regression kind of models, how it can work, and gradually we will take it up to the other models. Okay, so that is what we are planning. So as this particular series is more towards energy analytics, okay, so we are taking a data sets which is relevant for people who are practicing energy or managing a power plant and other things. Okay, so that the efficiency of the current power plant can be improved. Okay, and other things. Okay, so that is our plan. Okay, so the next session will be on next Saturday. Okay, Mr. Gokul will communicate the time. Okay, and he will share you the links. Okay, so please pass on the whatever codes and other things freely to your students also, or whomever is your colleagues or something like that. Okay, and if there are some doubts also, you can ask them to join the link. Okay, this is a free session which is being given by IAEMP Coimbatore chapter, and all these files, the Excel sheet, everything will be uploaded into a common drive, and it will be available for all of the participants for future usage. Okay, so if there are no questions, let me call it a day. Thank you so much for your participation.
Thanks. Thank you very much.
Participants, thank you. For the newly joined participants, I have added a link over here. Please provide your details and feedback about the session so that further communications we can send it to you. Thank you.
Okay, thank you. Bye-bye.
Okay, thank you all.
Thank you.